In section 1.2, we're going to work on solving rational equations. The term rational equations means solving equations that has fractions in them. But before doing so, let's just kind of go back and review solving basic linear equations. The steps to solving a basic linear equation is, first of all, we want to simplify each side of the equation first when starting. Here, for the first one, the left-hand side, we want to begin by getting rid of those parentheses. And we can do so by distributing the negative sign in. We would have 5x. This would become now a negative 2x and a minus 2. It's equal to, on the right hand side, we have some like terms we can combine. X plus 3x will give us 4x minus 5. Once the parentheses on the left hand side were removed, we now have like terms we can combine. 5x minus 2x will give us 3x minus 2, which is equal to 4x minus 5. And at this step, each side of the equation is as simplified as it gets. The next move would be to take and get all of your variables to one side of the equal sign. And so I'm going to do so by getting rid of the smaller amount of x's. So I'm going to subtract 3 x's from both sides. If we do this, the 3x and the negative 3x on the left-hand side cancel. So we're left with negative 2 equals 4x minus 3x will leave us 1x, or x, minus 5. We have now successfully moved all of our variables to the right-hand side, so that's where all of our attention should go. And now what we need to do is isolate the x. To get the x by itself, we want to get rid of this subtraction by 5. So we're going to go ahead and add 5 to both sides. So whatever I do to one side of the equation, I have to do to the other side. So we have negative 2 plus 5 is going to be positive 3 equals x, and then the negative 5 and the positive 5 cancel, and we get the solution x equals to 3. What that means is that the value of x equaling 3 is the value for the variable that we can substitute into this equation that will provide us with a true statement. One of the things that's nice about solving equations is you should always be able to tell whether or not your answer is correct by simply checking by back substituting in. So while we're not going to check all of these, let me at least show you this one so we can see what it would look like. So to check our solution, what I'm going to do is everywhere I see x in the original statement, I'm going to replace it with the number 3, and let's see if we get a true statement. So this would look like 5 times x, so 5 times 3, minus 2 times 3 plus 2. And now we want to see, is this going to be equal to 3 plus 3 times 3 minus 5. Okay, does that work? Well, to compute this, let's follow order of operations. So we have 5 times 3, which is 15, minus, in the parentheses, 2 times 3 would be 6, plus 2, equals on the right-hand side, we're going to have 3 plus 3 times 3 is 9, minus 5. Inside the parentheses, 6 plus 2 is 8. 3 plus 9 is 12, minus 5. And 15 minus 8 is 7. And 12 minus 5 is also 7. So we plugged the value x equals to 3 into the equation. And sure enough, it did result in a true statement. And that verifies that the solution to this equation is indeed x equals to 3. Let's now take a look at the next example. We have x divided by 5 equals x divided by 6 plus 1. Usually whenever I do this kind of a question in class, I'll start by asking the class to raise their hands to see those students who actually like working with fractions. And oftentimes I don't get very many hands raised because I think people for some reason have an inherent fear or just dislike of fractions. But you know, they're real numbers like any other number. They're not that bad. And we're going to work with them quite a bit in this class. So let's take a look at this equation here. The thing that I think that most of you would probably recognize immediately when you look at it is, okay, sure enough, we do have fractions. We have x divided by 5 and x divided by 6. The easiest way to solve equations that have fractions in them is to get rid of the fractions in the very beginning by multiplying both sides of the equation by the LCD, or the lowest common denominator. Okay? If we look at or it's also called the least common multiple. The least common multiple of 5 and 6, which represents the smallest number that both of them can be evenly divided into, I should say, would be the number 30. So what I'm going to do is let's multiply every single term in our equation by the LCM. So we're going to do 30 times x over 5 equals 30 times x over 6. And whenever you're doing this, you need to make sure you're multiplying every single term in the equation by that LCM. So even though this 1 is not itself a fraction, you still need to multiply it by that number 30. Now what's going to happen is, if you remember how fraction multiplication works, when we have that 30, we can think of that as essentially 30 over 1 whenever you're dealing with a fraction. And now we get some simplification. Notice that we can cancel the common factors here. 5 goes into itself once. 5 goes into 30 6 times. So this first term is going to reduce to 6x over 1. Because now once you reduce, you multiply across the tops, you multiply across the bottoms. So we get 6x over 1, which is just the same thing as 6x. This is equal to, on the right hand side, same thing, this next term we can simplify. I'm multiplying fractions. There's a common factor here. 6 goes into itself once. 6 goes into 30 5 times. So now we're left with 5 over 1 times x over 1. And that's simply going to produce 5x plus 30 times 1 is going to be 30. So just by doing that, we've now arrived at an equation that contains no fractions. And that makes us happy, right? So fractions are totally gone by using that LCM. From here, it's now like one of our basic linear equations. We're going to finish off by solving it. Each side is simplified. The next move would be to bring all of the variable to one side. So let's get rid of the smaller amount of x's. Let's subtract 5x from both sides. And we're left with the following. 6x minus 5x is going to be 1x, or x equals 5x minus 5x is 0. And so we simply get x equals to 30. If you're hesitant or if you're not sure, we can always check it. Everywhere we see an x in the original equation, let's check this one too. We're going to plug in the number 30. So is it the case that x, or 30 divided by 5, is that really going to be equal to x divided by 6? That is 30 divided by 6 plus 1. Well, 30 divided by 5 is 6. 30 divided by 6 is 5. And then, yes, 5 plus 1 does give us 6. So we plug in the value x equals to 30. We get the true statement that 6 equals to 6. And that verifies that x equals to 30 is indeed the solution to this equation. So while this equation actually did have fractions in it, this is an example of a rational equation, the denominators themselves were just constant numbers, like the numbers 5 and the number 6. Usually when we say a rational equation, we include the possibility where we might actually have the variable in the denominator. Okay? We'll solve them with the same procedure of the LCM, but there's a couple little things we have to be careful with here. With rational equations, you always have to check your solutions because it's possible to end up with what's referred to as extraneous solutions. An extraneous solution is one that comes out as a result of following the rules of algebra, but it's a value that really does not solve the equation at all. Okay? There's two ways you can check to see if you have a extraneous solution when dealing with rational equations. The first method would be just to simply plug it in at the end. You can go ahead and solve all of it like we just did, and then plug it in at the end to see if it gives you a true statement. The other way, which I believe is a much more efficient way and something that will help you later on down the road, is to look for what we call the list of restrictions. And the restrictions are going to come from some restrictions we have on algebra, or actually not algebra, but arithmetic rather. One of the things that we know arithmetically that we're not allowed to do is we cannot divide by 0, right? So division by 0 is undefined. So whenever you start off with an equation like this, take a look at your denominators and solve for where any one of those denominators could be equal to 0. For instance, with the first denominator, we have that 2x would be equal to 0. If we solve this, divide both sides by 2, precisely when x equals to 0. Similarly, if I look at the denominator of 3x, when could that be equal to 0? Well, we solve it out. We get that same value, x equals to 0. And on the right-hand side, this is just the number 3, right? It's just a constant. You don't need to worry about that. That's never going to be 0. It's always just going to be the value 3. But one thing that we do see is that if we were to try and plug in the number x equals to 0 into this equation, it would cause at least one of our denominators to be 0, which would be undefined. Therefore, we will know that a value like x equals to 0 could never be a solution to this equation. And so we're going to call that our restricted value. Once you have your list of restrictions, it's simply a matter of going ahead then and solving the equation and just double checking to make sure that any proposed solutions you get don't end up on that list of restrictions. If they are, then those are going to be your extraneous solutions and you wouldn't even have to go back and plug them in. Okay? If you solve it out and you get a value of x that's not on the restricted list, then as long as your algebra is good, then that will be a solution. So let's see if we can solve this equation, and we're going to start it off exactly the same way. So we want to begin by finding the LCM of all of our denominators. So let me just recopy the problem down first. So these are our denominators. We have 2x, 3x, and 3. The least common multiple of 2x, 3x, and 3 is going to be the smallest algebraic quantity that's evenly divisible by all of those 3 terms, and that's going to be the expression 6x. So every single one of those expressions, 2x, 3x, and 3, can all evenly divide into 6x. Furthermore, there's nothing smaller that would work. So now that we know what the LCM is going to be, let's do the same thing. We're going to multiply every single term in our equation by 6x. And we can think of it as 6x over 1. And what that should do for us is that should eliminate and get rid of all of these fractions. Over here with the first term, notice that the x's are going to cancel. 2 goes into 6 3 times. And so what we're going to be left with is 3 times 7, which is 21. The denominator would be 1, and 21 over 1 is just 21. Minus, let's look at the next term. Again, here the x's cancel. This x cancel with that x. 3 goes into itself once. 3 goes into 6 twice. And so we have 2 times 5, which is 10, over 1, which is just 10, equals, on the right-hand side, again, we can reduce first before multiplying. 3 goes into itself once. 3 goes into 6 twice. We're still going to have the x there. So we have a 2x times 22. 2x times 22 should be 44x over 1, which is just 44x. So far, so good. We've now gotten rid of all of our fractions, and now we just solve the resulting linear equation. Simplify the left-hand side. 21 minus 10 is 11. equals to 44x. And then to get x by itself, we're now just going to divide both sides by 44. So we get x equals 11 divided by 44. This will simplify. Both numerator and denominator are divisible by 11. 11 goes into itself once. 11 goes into 44 4 times. Okay. This was a rational equation, so we have to be very, very careful here. We either need to substitute this x value back into the original expression, or just do a quick check to see if it was on our restricted list of values. The only restricted values we had for this equation was x was not allowed to be 0, and so 1/4 would be allowed, and that means that that will be a solution to our rational equation. So the solution to this equation is simply x equals to 1/4. Let's take a look at the next one. We want to solve 3 divided by x plus 4 minus 7 equals -4 divided by x plus 4. We're going to do it exactly the same way. Anytime you solve a rational equation, my advice would be start off with a list of restrictions. So we're simply going to take any of the denominators and set them equal to 0. Here we end up with just one expression. The only denominator we have is of the form x plus 4 equals to 0. To get x by itself, we would subtract 4 from both sides, and this would produce x equals -4. So if we were to plug -4 in from what we've just shown, when you plug -4 into this equation, that will give you a division by 0, which is not allowed. So for this equation, our restricted value is going to be x cannot be equal to -4. So let me just kind of box that there. That's our restricted value. Now we're going to go ahead and solve the equation. We want to do the same thing we've been doing. We need to find the LCM of all of our denominators. Well, here there's just one term. That one term is x plus 4. So it is going to be its own LCM. We're now going to multiply every single term in the equation by x plus 4. So I'm going to recopy it here. So I'm going to multiply the first thing by the expression x plus 4. I'm going to multiply this by x plus 4, and I'm going to multiply this by x plus 4. Then when you're using it with a fraction, it's helpful to put it over top of 1. And now let's go ahead and reduce this. Notice that this x plus 4 cancel with this x plus 4, goes into itself once. So we're going to get 1 times 3 over 1 times 1. So the first expression is 3. Here, we can just distribute the -7 in. That's going to give us a -7x minus 28 equals, over here, the x plus 4s would cancel. They go into itself once. And the right-hand side is going to be just -4. We now need to solve this for x. First of all, on the left-hand side, we can combine some like terms. 3 minus 28 would give us -25 equals to -4. The next step is we can add 25 to both sides. So add 25 to both sides. These cancel. We get -7x equals -4 plus 25 is going to be a positive 21. And then lastly, divide everything by -7. The -7's here cancel, and we get x equals 21 divided by -7 should be equal to -3. And I was a little bit hasty on drawing that, but again, before I go ahead and say that that is the solution, remember you need to either plug it back in to double check it, or we need to check it against our list of restrictions. The only restricted value we had for this problem was x could not be negative 4. Therefore, x equals to negative 3 will be a solution. Again, in my opinion, checking it against a list of restrictions is by far the easiest way to show your work, to make sure you have a solution. This one's not too bad, though. We could very easily do the check as well, if you're curious. If we plug negative 3 into this equation, here's what we would get. 3 divided by negative 3 plus 4 minus 7. That should be equal to negative 4 divided by negative 3 plus 4. So we're checking to see, does x equals to negative 3 really work? Well, in the denominator here, negative 3 plus 4 is a positive 1. So that's going to be 3 over 1 minus 7. Again, same thing over here. Negative 3 plus 4 is positive 1. 3 divided by 1 is 3. Minus 7 equals negative 4. And 3 minus 7 is negative 4. So it does end up checking out. So we plugged negative 3 in, we get a true solution, a true statement, so we know that it is indeed the solution. But again, we would have known that simply by checking it against our list of restrictions to see that it was not on there. Let's take a look at the next example. We have 3 divided by x plus 3 is equal to 5 divided by 2x plus 6 plus 1 divided by x minus 2. And one of the things that's also going to be helpful too, as a first step, is if your denominators are not factored, factor your denominators first. It'll not only help for the LCM, but it might also save some work when you're doing the restrictions. In particular, if we look at this denominator here, 2x plus 6, this actually factors as 2 times x plus 3. So instead of calling it 2x plus 6, we can put it in factored form, and we see that it's 2 times x plus 3. Let's now look for our list of restrictions. We're going to take any of the denominators that have an x variable in it and set them equal to 0. So we want to know when is x plus 3 equal to 0, when is 2 times x plus 3 equal to 0, and when is x minus 2 going to be equal to 0. For the first one, we simply subtract 3 from both sides, and we get x equals to negative 3. Over here, easiest way is divide by 2 first. We get x plus 3 equals to 0, and then again subtract 3 from both sides. So that gives us the same restriction, x cannot be negative 3. And for the last one, add 2 to both sides, and we get x equals to 2. So for our restricted values this time, we get two numbers that will not work. So x will not be allowed to be negative 3, and also x will not be allowed to be positive 2. Because those are the values that if we plug in, will give us a division by 0. Therefore, everything would be undefined, and we wouldn't be able to actually get a true statement out of it. Okay, so we now know our restrictions. The next step is we want to clear our fractions by finding the LCM of our denominators. We want the LCM of x plus 3, of 2 times x plus 3, and also x minus 2. And again, having it in factored form, this is going to make things a lot easier for us. If you think of kind of like the coefficients of the factors, it's like a coefficient of 1, 2, and 1. So we need to have a 2 out in front. We have one factor of x plus 3 is the most that it appears. And then we also have a factor of x minus 2. So the LCM is going to be 2 times parentheses x plus 3 times parentheses x minus 2. And it's this expression that we're going to multiply to every single term in our equation. So let me just kind of go ahead and we're going to copy it out. So we have 3 divided by x plus 3, leave some room here, 5 divided by 2 parentheses x plus 3 plus 1 divided by x minus 2. And now let's multiply every single term on both sides of the equation by that LCM. So we're going to multiply by 2 times x plus 3 times x minus 2 over 1 times by 2 times x plus 3 times x minus 2 over 1 times 2 times x plus 3 times x minus 2 all over 1. Then simplify before you multiply. Here with the first expression we see that the x plus 3's are going to cancel. So those cancel. We're going to have 3 times 2 times x minus 2. 3 times 2 I know is 6. And I'll leave the x minus 2 alone for right now. Equals, for the next term, notice that the 2's cancel. The x plus 3's cancel. And we simply get left with 5 times x minus 2. Plus, over here, the x minus 2's cancel, and we're going to have 1 times 2 times x plus 3, which is 2 times parentheses x plus 3. Okay. And again, it's at this step we're now happy, our fractions are totally gone, and we have a basic linear equation to solve. We're going to continue to solve this. We're going to get rid of the parentheses where we're going to distribute. That should give us a 6x minus 12 equals, distribute the 5 in, 5x minus 10, plus distribute the 2 in, we get 2x plus 6. We can now combine like terms on the right hand side. 5x plus 2x will give us a 7x. A negative 10 plus 6 would give us a negative 4. The next step would be to bring all of our x's to one side. So I'm going to get rid of the smaller amount. Let me subtract 6x from both sides. Cancels on the left hand side. So we get negative 12 equals 7x minus 6x is 1x minus 4. The x is on the right hand side, so we have to simply just add 4 to both sides to solve it. Negative 12 plus 4 is negative 8. Equals to x. So we have a value for x. Just a quick check. Is this value on our restricted list? Once again, the answer is no. So that will be our solution. So the solution to this rational equation is going to be negative 8 equals x. Let's take a look at the next example. We have yet another rational equation. Thankfully for us, the denominators are already factored to begin with, so we don't have to worry about factoring everything first. We can move right on to the restrictions. Let's take each denominator, or actually, not only, you don't have to really necessarily set each denominator equal to 0, but you need to set each of those different factors equal to 0. So we have the x plus 2 equals to 0. The x minus 2 equals to 0. And for as long as you have the denominators already factored, then it's simply a matter of setting each factor equal to 0. But notice that these are already kind of repeated. We already set x plus 2 equal to 0 from before, and we've already set x minus 2 equal to 0. So we just have to solve each one of these. We would subtract 2 from both sides, and we find that one restricted value is going to be x equals to negative 2. If we add 2 to both sides, we'll see that the restricted value will also be x equals to positive 2. So x cannot be negative 2, and x cannot be positive 2. So those are our restricted values. Let's now go ahead and see if we can identify the LCM. So we want the LCM of x plus 2 x minus 2, and then x plus 2, x minus 2. We have 3 terms. The most factors of x plus 2 that show up in any expression is a tie between these two, but the most amount is we have 1 factor of x plus 2. Similarly, the most factors in any individual term that contain x minus 2 is a tie. Each one of those has 1, so that most amount would be the 1 power or the 1 factor of x minus 2. So this is going to be our LCM. It's going to be x plus 2 times x minus 2. We're now going to go ahead and multiply every term in the equation by that LCM. So to every single term, we're going to multiply by the LCM. And to help work with a fraction, I'll put it over top of 1. And this is what we get. For the first term, the x plus 2's cancel. So we're left with 5 times x minus 2 plus, here notice that the x minus 2's cancel, so we're going to be left with 3 times the quantity x plus 2, and on the right hand side the x plus 2's cancel, the x minus 2's cancel, so we're going to be left with 12 times 1, which is 12. We've cleared fractions. Now we're going to solve the resulting linear equation. Let's distribute. We're going to get 5x minus 10 plus, distribute the 3 in, 3x plus 6 equals to 12. Combine like terms on that right hand side. 5x plus 3x is 8x. Negative 10 plus 6 would be a negative 4 equals to 12. We would then add 4 to both sides. We get 8x equals to 16. Divide by 8, divide by 8. And we get the solution x equals to 2. However, this is what we were on the lookout for. This value, x equals to 2, was on our restricted list. And what that means is that this is an extraneous solution. Because after all, we wouldn't be able to plug x equals to 2 into the original equation because it would result in division by 0. Okay? So what does that imply for the solution set? Well, again, as we said a moment ago, don't box this, don't put this as your final answer. X equals to 2 does not work. It's the only proposed solution that we came up with, and because it itself doesn't work, what that means is that this particular equation will have no solution. So for this equation, there is no solution. You can write that out in words. You can either write no solution. Usually I'll abbreviate it no SOLN for solution, or more commonly you'll see people use the empty set notation, which also means no solution. So no matter what we do, there is no real number. There is no value of x that you could ever plug into here to get a true statement or to get both sides to be equal. Let's take a look at the next one. Again, we want to solve this rational equation. As we hinted at earlier, the first step that makes things much easier is if you factor all of the denominators first. X plus 3 is linear, it's factored, it can't do anything more. Same thing with x minus 2. But we can rewrite x squared plus x minus 6. This one actually factors, it's a trinomial. It's going to factor as an x and an x a plus and a minus, and it's going to be a plus 3 and a minus 2. So this denominator, let me just I'll kind of cross it out. We're going to work with it in its factored form, which is x plus 3 times x minus 2. Now that all of the denominators are factored, let's begin by finding our restrictions. The different unique linear factors that appear in denominators, we have some terms that look like x plus 3's. We also have some factors of x minus 2 in denominators. If we subtract 3 from both sides, we get x equals to negative 3. Over here, if we add 2, we get x equals to 2. So those are our restricted values. X cannot be equal to negative 3, and x cannot be equal to positive 2. Those values of x would produce division by zeros in the denominator, which would leave the expression undefined. The next step now is we want to find our LCM. So let's find the least common multiple of our denominators. The LCM of x plus 3, x minus 2, and x plus 3 times x minus 2, that's going to be equal to x plus 3 times x minus 2. Once we've identified it, we're now going to multiply every single term in the equation by that LCM. Let's multiply this by x plus 3 times x minus 2 over 1 times x plus 3 times x minus 2 over 1 times x plus 3 times x minus 2 over 1. Simplify first before multiplying. The x plus 3's cancel here, leaving us with 6 times x minus 2. Over here, the x minus 2's cancel, leaving us with negative 5 times x plus 3. And on the right-hand side, for this term, the x plus 3's cancel, the x minus 2's cancel, so we're simply left with negative 20 times 1, which is going to be negative 20. We can continue to solve. Let's distribute. 6 times x is 6x. 6 times negative 2 is negative 12. Negative 5 times x is negative 5x. Negative 5 times 3 is negative 15. And this is going to be equal to negative 20. Combine like terms on the left-hand side. 6x minus 5x is 1x. Negative 12 minus 15 is negative 27. Equals to negative 20. And now add 27 to both sides. These cancel, and we get x equals, here, negative 20 plus 27. That should give us positive 7. We check, x equals to 7 is not on our restricted list, so that indeed is the solution. The solution is x equals to 7. One of the things that we've seen already is some different types of classes of equation. We say that an equation is a conditional equation if it's true for some values of x but not all values of x. Okay, so true for some, but not all values of the variable. So conditional equations are ones that have solutions, but not every real value of x does work. Like, for example, if you look at the equation x plus 3 equals to 5. This is an example of a conditional equation. It would have the unique solution x equals to 2. An identity is an equation that's true for all values of the variable. So any real number would work. An example of an identity, for example, would be the equation 2 parentheses x plus 3 equals 2x plus 6. You might recognize this as the distributive law, but we know that on the left-hand side expression and the right-hand side expression are always equal via the distributive law. So that would work for all real values. It doesn't matter what value of x you plug in, the left-hand side and the right-hand side will always be equal to each other. So the solution set, we would say the solution would be all real numbers, and we would call this type of an equation an identity. The last type of equation we have is what's called a contradiction. And these are equations that have no solution. Okay, we saw one of these earlier. If we just scroll up to this one right here, this was an example of an equation that had no solution. So this type of equation we refer to as a contradiction. Another easier example of a contradiction would be like the equation x equals x plus 1. This is yet another example of an equation that has no solution. And the reason for that is if you compare the left-hand side and the right-hand side, there is no real number that is equal to one more than itself. That would be impossible. Those two quantities could never ever be equal. And we would call these types of equations contradictions.